butter is one of the simplest food products by ingredient count, it is almost entirely milk fat, but the industrial process that transforms raw, whole milk into a shelf-stable, precisely textured, consistently flavored block of unsalted butter involves more separation, temperature management, and mechanical precision than most people would expect from something so basic. Modern butter factories process millions of liters of milk every week, and the production line that handles it runs continuously. This is the complete process from incoming raw milk to wrapped and palletized finished product. It begins at the receiving dock where tanker trucks carrying raw whole milk arrive from dairy farms and cooperatives. Raw milk is not a uniform product. Its composition varies by breed of cow, season, feed quality, and stage of lactation. The fat content in particular can range from around 3% to over 5% depending on the herd and the time of year. For a butter manufacturing facility, fat content is the most commercially significant variable in the incoming milk because butter yield is directly proportional to fat content. More fat in the incoming milk means more butter produced per liter processed. The fat content of every incoming tanker load is measured at receiving using infrared analysis equipment that gives the plant accurate compositional data within minutes of arrival. This data is used both for payment calculations. Dairy farmers are typically paid in part based on the fat content of their milk. And for production planning, since the cream separation system downstream needs to be adjusted for incoming milk composition to produce cream at the target fat percentage. Before any milk enters the production system, it is sampled and tested for antibiotic residues, a mandatory receiving check at every dairy processing facility. Milk containing antibiotic residues from treated animals must not enter the food processing system. Rapid test kits give a result within minutes, and any load testing positive is rejected and returned without being unloaded. Loads that clear the antibiotic screen, along with a temperature check and basic organoleptic assessment, are approved and the truck is connected to the facility's receiving lines. The milk is pumped from the tanker through receiving lines and into large raw milk storage silos, temperature-controlled stainless steel tanks that hold the milk at chilled temperature, typically around 34 to 38 degrees Fahrenheit, while it awaits the next processing step. From raw milk storage, the milk moves into the pasteurization and separation system, and these two processes are closely linked in the production flow. Pasteurization of the incoming raw milk, or of the cream separated from it, depending on the plant's process design, is a legal requirement in most countries for commercially produced dairy products. For butter production, many facilities pasteurize the cream after separation rather than the whole milk before it, because the cream fraction is what continues through the butter making process, and pasteurizing the cream allows the heat treatment to be targeted precisely at the product that will become butter. The pasteurizer is a plate heat exchanger, a compact machine built from a stack of thin, corrugated stainless steel plates through which the cream and a heating medium flow on alternating sides, transferring heat from the heating medium to the product across the thin plate surfaces with very high efficiency. The cream enters the pasteurizer cold, is heated rapidly to the pasteurization temperature. For high temperature, short time pasteurization, this is typically 161 degrees Fahrenheit held for 15 seconds, then is immediately cooled back down as it passes through the cooling sections of the same plate exchanger. But before pasteurization, the whole milk must be separated into cream and skim milk. The separation happens in a centrifugal cream separator, a machine that spins the incoming milk at very high rotational speeds inside a bowl, containing a stack of conical disc plates. As the milk spins, the centrifugal force, thousands of times greater than gravity, pushes the denser skim milk fraction outward toward the bowl wall, while the less dense fat globules migrate toward the center axis of the spinning bowl. Two separate outlets collect the two fractions continuously. Skim milk exits from the outer discharge, and cream, now concentrated to a fat content significantly higher than the incoming whole milk, exits from the inner discharge. The fat content of the cream exiting the separator is controlled by adjusting a flow control on the cream outlet. More restriction produces higher fat cream, less restriction produces lower fat cream. For butter production, the target cream fat content is typically between 35 and 40% fat, a level that is high enough for efficient butter churning, but still fluid enough to be pumped and handled easily through the processing system. Separated cream, now pasteurized and at the target fat percentage, moves into temperature-controlled cream aging tanks, and this holding step has a specific technical purpose that directly affects the quality and texture of the finished butter. Milk fat is not a single compound. It is a complex mixture of triglycerides with different melting points, ranging from very low melting fractions that remain liquid, even at refrigerator temperatures, to higher melting fractions that are solid at room temperature. For butter to have the right texture, firm enough to slice cleanly from a cold block, spreadable when brought to room temperature, smooth rather than waxy or greasy, the fat crystals in the butter need to be in the right physical form when the product is packaged. The crystal form of milk fat is determined by its thermal history, the temperatures it has experienced, and the rate at which it was cooled or heated through its crystallization range. The cream aging process in the holding tanks, which keeps the cream at a low, controlled temperature. typically between 40 and 50 degrees Fahrenheit, for a defined period of time, promotes the formation of the stable fat crystal form required for the churning process and for the finished butter texture. Skipping or shortening this aging step produces butter with a softer, sometimes greasy texture that doesn't meet the quality standard of a properly crystallized product. After aging, the cream is pumped to the continuous butter churn, the machine that performs the core physical transformation of the entire process. A continuous butter churn is a large horizontal cylinder, sometimes with internal agitation elements, through which the cream is continuously fed and continuously discharged as butter and buttermilk in separate streams. The principle of butter churning is essentially the mechanical destabilization of the fat globules, emulsion, and cream. In fresh cream, the fat exists as individual globules, tiny spheres of fat surrounded by a protein and phospholipid membrane that keeps them dispersed in the watery phase of the cream. When the cream is agitated mechanically, the globule membranes are disrupted, the fat is released, and the released fat globules begin to coalesce, clumping together into progressively larger masses of fat. As this coalescence continues, two distinct phases emerge: butter grains, irregular masses of coalesced fat, and buttermilk, the remaining watery phase containing the milk, proteins, lactose, and the residual components from the fat globule membranes. The transition from cream to these two phases happens over a matter of minutes in a continuous churn operating at the correct temperature and throughput rate. The temperature of the cream at the churn inlet is one of the most critical operating parameters. Too warm and the fat is too soft to form discrete grains. Instead of churning into separate butter grains and buttermilk, the fat smears into a continuous mass that clogs the churn and produces a product with the wrong texture. Too cold and the fat is too hard, the globules don't coalesce efficiently and the churning yield drops. The correct inlet temperature varies with the fat composition of the cream and the season, because the melting point profile of milk fat shifts with diet and season, and the plant's production team adjusts the cream inlet temperature accordingly. From the churn, the butter grains and the buttermilk exit together into the buttermilk separation section of the continuous butter maker, a stage where the buttermilk is drained away from the butter grain mass. The drained buttermilk is collected and moved to its own processing line. It is a commercially valuable byproduct used in food manufacturing, animal feed, and as a cultured dairy ingredient. The butter grain mass that remains after buttermilk separation still contains a significant amount of residual buttermilk trapped within and between the grains, and this residual liquid needs to be washed out before the butter is worked into its final form. The washing stage passes chilled water through the butter grain mass to dilute and remove the residual buttermilk. Buttermilk contains lactose and milk proteins that, if left in the butter, reduce its shelf life. The lactose provides a substrate for microbial growth, and the proteins contribute to off-flavor development over time. For unsalted butter, which has no salt to act as a mild preservative, thorough washing is particularly important for achieving the product's target shelf life. The wash water that drains from the butter grain mass carries the dissolved buttermilk components away, and the washed butter grains emerge with a significantly reduced buttermilk content. The washed butter grains now enter the working section of the continuous butter maker, the stage that converts the loose, granular mass of butter grains into the smooth, continuous, homogeneous texture of finished butter. The working section subjects the butter grain mass to mechanical compression and kneading between rollers or through auger systems that press and fold the material repeatedly. This mechanical working serves two simultaneous purposes. First, it expels the remaining washed water from the butter mass. The water content of the finished butter is a closely regulated parameter, with most butter standards specifying a maximum water content of 16%, and the working process controls how much water remains in the product by the intensity and duration of the mechanical action applied. Second, the working breaks down the granular structure of the butter grains and works the fat into a continuous, uniform mass with the smooth, waxy texture of the finished product. The visual transformation through the working section is dramatic. The loose, granular, somewhat pale yellow grain mass enters, and a smooth, continuous, deeply yellow butter paste exits, with no visible grain structure remaining. The yellow color of butter, which varies in intensity from pale straw yellow to deep golden depending on the season and the cow's feed, comes from beta-carotene, a pigment present in the milk fat that cows derive from green pasture. Summer butter from grass-fed cows tends to be significantly more deeply colored than winter butter from cows on stored feed. Some butter manufacturers add a small quantity of beta-carotene or annatto color at this stage to standardize the color across seasonal variation and maintain a consistent appearance in the finished product year-round. For products labeled as natural or without added color, the seasonal color variation is simply accepted as a natural characteristic of the product. For unsalted butter specifically, no salt addition step occurs. The butter exits the working section as the finished product. For salted varieties produced on the same line, fine salt would be introduced into the butter mass during the working stage and worked into uniform distribution before the product exits the butter maker. In the unsalted production run, the work butter exits the continuous butter maker directly into the packaging system. The finished butter is at a temperature, typically between 55 and 65 degrees Fahrenheit, that makes it workable for the packaging equipment, soft enough to be extruded or deposited into the molds and packaging that shape the finished block, but firm enough to hold its shape after packaging without slumping or deforming. The transition from the butter maker outlet to the packaging machine inlet is managed through insulated and sometimes temperature-controlled transfer lines that keep the butter at the target temperature range throughout. The packaging line for retail butter blocks operates at high throughput, and the machinery involved handles the butter with a combination of speed and precision that is impressive to watch in operation. The most common retail format for unsalted butter in the United States and many other markets is the 1-pound block divided into 4 quarter-pound sticks, each individually wrapped in parchment or foil laminate wrapper and then combined into a folded paperboard carton. The butter is fed from the transfer line into the packaging machine, which extrudes or deposits the butter into a continuous log or into individual portion molds depending on the machine design. In stick butter packaging, the butter is extruded as a continuous rectangular log at the target cross-sectional dimensions of a butter stick, which is then cut into individual stick lengths by an automated cutting blade operating on a timed cycle. Each cut stick is transferred to the wrapping station where a pre-cut sheet of parchment or foil laminate wrapper, printed with the brand name, net weight, and other required label information, is folded around the stick and heat-sealed or crimped at the ends to form a tight, fully enclosed wrap. The folding and sealing sequence in a commercial butter wrapping machine happens in a fraction of a second per stick, with the sticks moving through the wrapping sequence on a timed conveyor without stopping. 4 individually wrapped sticks are then grouped and pushed into the paperboard carton, the outer retail package, which is assembled from a flat, blank by the carton erecting mechanism integrated into the packaging line. The filled carton is closed and sealed at the top flap by adhesive or tuck closure, and the completed retail package, 4 wrapped sticks in a sealed carton, exits the packaging machine and moves on to the outbound conveyor. Every completed carton passes through a check weigher that verifies the net weight of the package against the declared 4 quarter-pound specification. Packages outside the tolerance range are automatically diverted. Each carton then passes through a metal detector positioned on the outbound conveyor immediately after the check weigher, operating at the sensitivity level required by the facility's Hakesby plan. Both the check weigher and metal detector log every reading and divert event continuously as part of the facility's food safety documentation. Accepted cartons move to the case packing station where automated equipment groups them into the shipping case count, typically 12 or 20, 4 cartons per case, depending on the retailer specification, erects the case from a flat blank, fills it, seals the top flaps with applied adhesive, and applies a printed production code carrying the manufacturing date, shift, and best before date. The best before dating on unsalted butter is typically between 60 and 90 days from the production date at refrigerated storage conditions, reflecting the product's susceptibility to oxidative and hydrolytic flavor changes in the absence of the mild preservative effect that salt provides in salted varieties. Cases move from the coating station to the palletizer, robotic or mechanical systems that stack cases onto wooden pallets, and program configurations optimized for load stability and truck loading efficiency. Completed pallets are stretch wrapped, labeled with warehouse routing and distribution information, and transferred by forklift or automated guided vehicle to the refrigerated finished goods warehouse, where the product is held at refrigerated temperature until it enters the cold chain distribution network. From the warehouse, butter pallets enter refrigerated distribution, temperature-controlled trucks maintaining the product at or below 40 degrees Fahrenheit from the facility loading dock through to the retail receiving dock. The cold chain is continuous from packaging to retail display because butter at elevated temperatures softens, loses its shape, and begins developing off flavors through fat oxidation at a rate that significantly shortens its practical shelf life. From raw whole milk arriving in a tanker to wrapped and palletized unsalted butter blocks leaving the refrigerated warehouse, the process moves through receiving, separation, pasteurization, cream aging, continuous churning, buttermilk separation, washing, working, and packaging in a connected, uninterrupted sequence. The simplicity of the finished product, nearly pure milk fat, stands in contrast to the precision and control required at every stage to produce it consistently at industrial scale. That is the complete factory journey of unsalted butter, from raw milk to finished block. If this kind of detailed production process is what you come here for, a like makes a genuine difference to this channel. Subscribe for more factory and food manufacturing documentaries, and leave a comment telling us which dairy product, food ingredient, or production facility you want to see covered in full next. There is always more process behind the product than the wrapper suggests.